You ever, as a kid, just want to get an earthworm, cut it in half, and then grow each of the halves, and then you can cut each of them in half and grow each of the halves, and soon you have infinite earthworms? Well, it doesn't really work that way, but if it did, we'd be looking at a growth curve. Maybe even better would just get two guppies and leave them. So growth curves are our topic for this lecture. I want you to be able to define geometric, exponential, logistical growth, the carrying capacity, the intrinsic rate of increase, and density-dependent/independent factors. Be able to compare geometric growth, which we have briefly mentioned in the flea lecture. Be able to compare that with exponential and logistic growth curves. List the conditions necessary for exponential growth or for logistic growth. It really helps in the comparison thing. Identify certain limits to carrying capacity and use the equations for growth to predict future population sizes. Really just a plug and chug there. So growth curves. We want to be able to calculate how fast something will increase. First off, we need to know something called the per capita growth rate. Now, capita is a head, basically. It's a per head. But per individual, each individual only has one head in most sane organisms, Tiamat notwithstanding. But the per capita growth rate is how much a single individual can reproduce. So you can calculate that a few times. One of the easiest ways is just to take a population and calculate the per capita growth rate, also known as R, is equal to the births minus the deaths. Now that's really also including the immigration and the emigration. So basically all new things in a population versus all old things in a population, all things that are leaving the population. So when R is greater than 0, we can actually be comparing this primarily to 0. When R is greater than 0, it means the population is increasing. So even if R is just 0.001, the population is increasing. If R is less than 0, that means the population is decreasing. So a negative R, for example. If R is 0, then that means the population is at equilibrium and there is 0 population growth. So if immigration is essentially non-existent and emigration is high and births equal deaths, then we're really going to have a situation where the population is shrinking. So if there are a lot of births and not very many deaths, and immigration and emigration are about the same, we're going to have a case where the population is growing. So it's simple as that. So there are 3 types of population growth models we're going to look at here: the geometric, the exponential, and the logistic growth models. Each of them have their own equations, which we'll be going through pretty briefly, and that's going to turn out to, well, we're going to look at the terms dn, which is change in population size, dt, which is the unit of time, so change in units of time, n, which is the size of the population, and r, which is the per capita rate of increase, births minus deaths. So we can calculate how big the population will get in the next generation. So first off is the geometric growth model. This is going to work on things like annual plants or organisms that die out each year. So each generation is going to reproduce and die. So it'll have either a single reproductive event usually, or multiple reproductive events that don't overlap in growth. So you're not going to have multiple generations overlapping. What you're going to get is each yearly generation. That's what keeps it geometric. So we're going to calculate that as n sub t is equal to n sub 0 lambda to the t. Okay, n sub t is your population at time t. N sub 0 is your population when you started. Lambda here is the growth rate, is a geometric growth rate, very similar to R, really, but useful in a geometric growth thing. You can use R. And t is just the time. So it's each generation is going to raise that by 1 power. Essentially, that thing multiplies per year. And as you see, geometric growth rate can occur, the increase occurs over generations. So you have that first generation of phlox plants, the type of flowering plant with 5 petals, and you have maybe 1 or 2. Now those are each going to set a certain number of seeds, and each plant on average is setting 2.4 living phlox seeds. So the first generation there might be maybe one or two phlox plants, and then it's going to be 1 or 2 times 2.4177. So, and then you're going to multiply 2.4177 by that, and then by that, and then by that. So each year, the average number of new plants produced per plant means that each plant is producing more plants to increase the population. So here your lambda, as long as your lambda is greater than 0, it's increasing. So it's your population growth rate. Then you have the exponential growth. And the exponential growth assumes that R is at some maximal level, so the maximized intrinsic rate of growth. You've probably seen this term of exponential growth when looking at microbiology. And this is where we're going to have a very fast reproduction. So assuming that R is unlimited, you have the change in the population size over the change in time is equal to R sub max, just basically R as big as R can get, times the population size times e to the RT. That's the standard E that you would use in math. So letters are numbers, 2.178 or something. That's been a little while, but it's your standard E. It's irrational, but R max can be whatever that population is capable of if it can make as many offspring as it wants. N is your original population size. Here you have the R again and the T. So it's same R realistically. Otherwise, you're just confusing. So what this does is it's exponential, and it's assuming, of course, unlimited resources. Now, it doesn't actually ever really happen, but it can come pretty close. So it can come pretty close, and it's not going to happen forever. But if, say, the ice sheet melted in Europe, which it did, and the spruce trees now have all this extra land, which they did, then what happens is the spruce trees are essentially capable of they can just grow wherever. There's nothing limiting their growth rate, and you see an exponential increase in the number of spruce trees. Elephant seals are hunted to near extinction. And then they had all this habitat and all this prey, and suddenly the hunting pressure stopped. And when it did, they just reproduced as fast as possible. Elephants are another example where there was massive poaching, and the poaching was so bad that there was close to extinction for elephants, but parks were generated, and they had nearly infinite resources. And as you see, the elephant population went way up. Now, as you may know, the population of elephants has stabilized and decreased again because we brought poaching back. So that's the exponential increase. It's basically unlimited increase, unlimited resources. And as you know, at some point, these all are going to meet caps. Obviously, the world is not covered in spruce trees. The seas are not swarming with sea elephants and elephant seals, and the land is not completely covered with elephants. Then you have logistic growth, which is what really happens. 3, C, D. All right, logistic growth is what really happens. And that's going to assume these limited resources, and it incorporates what's called a population size carrying capacity. So the carrying capacity here, your change in population size over your change in time is equal to, again, you have that Rn, so the R max n, but then you're going to add this other thing, k for carrying capacity minus n divided by k. So as so R max n is the same thing as up here, R max n, but we're multiplying it by k minus n over k. So let's say n is close to 0. Well, then k minus n over k is going to be very, very small. And essentially, k minus n over k is, k minus n is going to be very small. So essentially, it's going to be close to k. And k over k is 1, in which case dn dt is basically equal to r max n times 1. And when r max n times 1, well, you look back, and that's close to the exponential rate of growth for a single population. So for a single generation. So yeah, that'll grow quickly. But let's say n is close to k. If k minus n and n is close to k, then that's closer to 0. So the population growth rate is going to get smaller as k minus n gets smaller. So the difference away from some carrying capacity, as that gets smaller, sensibly, you'll get a smaller growth rate. And what that leads to is these kind of sigmoidal curves with these limited resources. Limited. So the limited resources here, you have a Daphnia population in a laboratory culture. And as you see, the fitted curve there shows the decrease as they got closer and closer to what their carrying capacity is. Then you have the number of paramecium in a culture, which as it gets closer to population maximum, the reproduction rate slows. And that's the idea, is that the reproduction rate is slowing as crowding increases. What you actually see with the Daphnia, and you actually see larger organisms, is they tend to overshoot. So they're going to actually get to a point where k minus n is a negative number, and then this dn dt becomes a negative number likewise. So if n is greater than k, you get negative growth. Simple enough. So, oh man, there's way more deer than this campus can handle, is going to result in negative growth, i.e. the deaths are going to outnumber the births. And for a while, that's the tragedy that will bring them back down towards an actual carrying capacity or being similar to carrying capacity. Then there's how do you change these equations? Because it's not always the same. And it's, this is ecology. Exceptions are more common than the rules we make for them. It feels like that sometimes. Let's look at some changes. And first, let's look at the human problem. What happens with humans is you had a certain number of humans living on the planet. And in repeated times, humans would they take certain grasses like wheat or rice or barley or corn or millet. They would take these grasses and they would clear areas for the grasses. So the grass population would increase, and the humans could then eat those grasses' seeds. So what happened here was a change in carrying capacity. When humans moved from the hunter-gatherer lifestyle into the agricultural lifestyle, they changed carrying capacity. And likewise, they changed their reproductive growth, because now there is less time spent out hunting and more time spent sitting around. Now, you'll see a divot there around 1348 CE, and that's where humans got introduced to the bubonic plague, where population density was high enough to drive plagues. And we'll come back to that. We'll come back to that. But more recently, it's greater than an exponential rate. And since about 1800 or so, we've discovered so many new ways to increase the carrying capacity or just increase reproductive rate. Advances in obstetrics have reduced mortality of women. So now the reproductive rate has increased. Advances in fertility treatments have increased reproductive rate, although not much. People are just fine without them as a whole. Reduction in death. Increase in the number of children that survive through vaccinations for things like polio and measles and mumps. Increase in agricultural delivery, so delivering the agricultural products to population centers. All of these have changed the carrying capacity and have changed the ways that humans interact with the population, with the carrying capacity. So much the same way, organisms that discover a new niche will increase above what looks like a carrying capacity. Now, there are those who argue that the carrying capacity of humans is limited strictly by phosphorus, and that at some point we're going to run out of easy phosphorus, which is going to decrease productivity of crops, which decreases K, which means our N is greater than K, and we're going to have a massive population crash. Yeah, probably. So then you can also see fluctuations in R as As the population gets closer to carrying capacity, what happens is R goes down. So that's really the logistical model kind of, shown on a line. So not linear there, linear viewing of the logistical model, that R max in very low populations is really maximized, but you get competition for resources and your R max goes down. Get overcrowding, R max goes down. So this can be seen in the example here of Daphnia. So the per capita rate of increase changed as the density of Daphnia increased. So R can be changing. There's also the regulation of population growth. So abiotic factors are just things that are going to change randomly. So those are density independent factors. El Nino changed the rainfall on the island Daphne Major, which these ground finches were feeding on. They were feeding on seeds on Daphne Major, and suddenly the seeds were not as available. So the ground finch, due to this population independent factor, was unable to get enough seeds. And when they couldn't get enough seeds, the need for seed, the population crashed, as you see between 1976 and 1977 on this graph. You can also see the collared lemming. And what happened with them is they have these population fluctuations due to predators. And that's a biotic factor. It's also a density dependent factor. So density independent factors are things that will just happen regardless of the density of the population. So temperature shifts, wildfires, disasters, natural disasters specifically, meteor hitting the earth, didn't care about the density of dinosaurs first. Those are population independent. Population dependent or density dependent factors are going to be having more of an impact as population gets denser. So competition. Here we have some mosquito larvae, and they're living in a pond. They actually will compete to get oxygen at the surface. Now, if there are more mosquito larvae than there is available surface area, only some of them are going to be breathing. And if only some of them are breathing, obviously, only some of them are going to survive. Territoriality. When birds can't find a nesting site, birds can't nest. When they can't nest, they can't make eggs. Predation here. You have predation of a vole, and that vole, actually, that is the predator. It's going to be foraging more optimally when prey is more dense. The bubonic plague struck primarily cities because it's a density-dependent factor. It needs to spread from person to person by an infected flea. And it can't do that if there's only one person living out in the middle of the woods, maybe riding Walden or something like that. Okay, that was later, but either way. Influenza and, of course, COVID-19. These are density-dependent factors. One of my favorite quotes from the COVID era is that the deaths are not so bad if you just don't look at the blue states. Okay, so if you don't look at New York, California, Washington State was never that bad, but if you don't look at New York and California and Maryland and Virginia, then the deaths aren't so bad. Well, the argument there is really silly because, yes, the death rate in places like Montana and Wyoming, where testing doesn't even occur regularly because people are far spread out, the death rate is lower. In fact, we saw COVID-19 went straight through cities. So mainly it's cities that are getting affected, which provided the rallying cry, well, look, it's these Democratic governors of cities, Democratic mayors are the ones who are causing it to happen. If you took out all the deaths in cities, we barely have any COVID at all. Silly mayors. Yeah, well, you can correlate it with pizza shops too. The density of pizza shops is also a density-dependent thing. Disease tends to spread quickly in dense areas, unless you socially distance, of course, or just escape to the woods and film your lectures from far away. I've heard worse ideas. Here's actually something, a flu update and a coronavirus update, a little treat for you on the PowerPoints if you want to follow these density-dependent factors that may actually have an impact on the population. See you next time.